Hello and welcome to YMT211, Discrete Mathematics. We are still discussing Chapter 2. This is the second part of the chapter, addressing logic, and as I said in the previous video, we are just addressing the principles or the elementary parts. Now in the previous video we covered most of the elementary parts, yet we still have few things to discuss. We explained about assertions and the connectives and the operators that we use with assertions. We explained about the truth tables, evaluation of compound statements. Now today we will discuss about how we can actually address compound statements in a bit higher way or more advanced way. Now usually when we have compound statements, they are really not easy to understand while they are written in natural language, English-like, as the language that we are using now. Usually we human beings get stuck when the statements or the assertions are lengthy with a lot of operators connecting them. So for that case, instead of dealing with them in the natural language, what we do is we deal with them in symbolic representation. Let me just give you a quick example. You can access the internet from campus if and only if you are a student or you are not a visitor. Alright. How can we represent this statement? We can understand it in English, but it's complicated to be represented in this way and passed to the computer or to the machine to be addressed. In order for us, we decompose it to its components. You can access the internet from campus. This can be one part of an assertion. It's an assertion, actually. This is compound, of course. So this can be one part, primitive. You can access the internet from campus. So there are two possibilities in this case. You can or you can't. So true or false. Only if this is bidirectional. It's not bidirectional, actually unidirectional conditional statement or just if statement. If you are a student, let's take this part, leave the operator. You are a student. This is also another assertion. You could be a student or not, so true, false, or another operator. You are not a visitor. Good. So we have here one. Let me use the pen. We have one here. You can access the internet from campus. This is, let's say, P. Only if, leave if aside, it's an operator. You are a student. T. You are not a visitor. Now you are not a visitor. Take it as a rule, which is not actually an official rule, but in this case we use the positive statement or the positive structure of the statement. We don't use the negated structure. You are not a visitor. Use it. You are a visitor. All right. Assign them letters or symbols in this case. P, you can access the internet from campus. Q, you are a student. R, you are not, sorry, you are a visitor, not you are not, you are. Take it in the positive form. If you want to compose the whole compound statement, P implies Q or not R. R, you are a student, not R, you are not student. Q, you are a visitor. Q, you are a student. R, you are a visitor. And the negation of it, you are not a visitor. All right, so this is the composition, and it's quite clear. Just do not forget to add these parentheses because it applies to both of them now to ensure the precedence or the priority maintained. Now, if we translate these statements, it becomes actually easier for the computer to understand in terms of software and hardware, and that's why we usually do such thing. One more reason, sometimes we need to affirm the consistency of the system specifications. What does it mean? Let's look at this simple example. The automated reply cannot be sent when the file system is full. Let's assign to these symbolic letters or letters actually to get the whole assertion in a compound statement, or sorry, in a compound statement, just one compound statement. The automated reply cannot, leave cannot aside can, use it in the positive way, not the negated way. The automated reply can be sent. All right, we can refer to this by P. When it's also an operator, this one is if. So leave it. I'll explain it to you in a while. The file system is full. The file system is full is also another assertion. We can use Q. Now, in order for us to represent when, it is similar, very similar to if statement in this case, or the conditional statement, the implication. Now, I would just like to rephrase it. If I say the file system is full, I can refer to it by Q, and the automated reply can be sent, I refer to it by P. The easiest way for me to represent this, I would say Q implies not P. What does it mean? Now let me just show you in the written text, it's easier. P, the automated reply can be sent. I said earlier the automated reply can be sent. And then Q, the file system is full. These are the two assertions that we have. Only operators left, just one operator, two operators, the negation of the statement because we dropped cannot, and the conditional statement. Now, in order for us to represent the whole system specification in this case, in symbolic representation of logic assertion, we explained about the components. P, the automated reply can be sent. As I said, leave it in the affirmative or positive structure. Then we have also Q, the file system is full, and they are connected to each other using the conditional statement with the negation of P. So what we can say is the file system, if the file system is full, the automated reply, then the automated reply can't be sent, and that is much easier in symbolic representation. Q implies not P. If the file system is full, then the automated reply can't be sent, and that is how we represent it. All right, let's take another example when we have different specifications of the same system, and we see if they are consistent or not. As I said before, a few slides, I think 2 slides before this one, we explained about the consistency of a system. How can we check, or it's possible for us to check it when we have different messages or different assertions implying the same thing. Now look, the diagnostic message is stored in the buffer, or it is retransmitted. Well, we have the diagnostic message is stored in the buffer. This is the first assertion. And then we have an operator, or it is retransmitted, another statement. The diagnostic message is not stored in the buffer. We don't have any new statement here. We have the negation of this. Is stored, is not stored. We just negate the first one, so we don't have any other statement here for the time being. If the diagnostic message is stored in the buffer, then it is retransmitted. Well, if we represent the diagnostic message is stored in the buffer, if we say it is P, and the diagnostic message is retransmitted by Q, then what we can say, we have P or Q, and then we have not P, and then we have if P, or P implies Q. So we have something like this. P, diagnostic message is stored in the buffer. Q, the diagnostic message is retransmitted. The first assertion, compound assertion, P or Q. The second one is just the negation, or not P. The third one, P implies Q. Now, in order for us to know if the system specification or these specifications are consistent, we need to take the truth table. And we need to see if we can get consensus between these operations, and in that case, we will have a consistency in the system. What do I mean? Let me just add one statement, just one statement. If we add one here to the requirements of the system, the diagnostic message is not retransmitted. So we said the diagnostic message is transmitted, is represented by Q. Now we have not Q. Now having all these specifications will lead us to that, like, there is no possibility all of them will have a true value for P and Q in the truth table. We would not even have one single truth value for all of them at the same time in one field, just one field. So in that case, it's not possible for us to have all these as consistent statements. Now, what did I say? Just try to construct the truth table for all of them and see if you get an outcome that's true for all of them at the same time. Just monitor the fields of all of these. If you can get one true value for all of these at the same time in the same field somewhere, just one is enough. You can't. But for this one, you can. You can try it on your own and see. All right. How can we manipulate propositions in another way or other than just dealing with and or negation? Do we have other rules? Yes, we have. We have some simplification rules. We have basic identity rules, domination, idempotence, double negation, commutativity, associativity, and so on. We have also two important rules of De Morgan's laws. These are used for negation of and or. So oring, the negation of oring, and the negation of anding for two or more actually operands. Operands here, symbolic representation of an assertion. We have also distributive law and absorption law, and we will see them in tables. That will be much easier. But before we go to the tables and explain about the essence of all these rules or laws, let me tell you a few things. I explained about those in the previous video. However, let me just get back to it and enlighten you about a few things. Now, if we have equivalency, and I said I will speak about it later on. If we have an equivalency, means what? P and Q are separate assertions, but if they have the same truth value, then we can call them equivalent in this case, not equal, equivalent. Why? Because P may be generated from a compound statement, and Q also can be generated from other compound statement. They don't match in the realization. That means their implementations are not equal. I said they may be. Maybe they are equal, maybe they are not, but generally not. That's why we say equivalent. They produce the same truth table, after all, the same outcome in their truth table. And in that case, in order for you to say they are equivalent, what you need to do is you need to check if P implies Q and Q implies P, or if and only if P implies Q. So this is the biconditional statement. In that case, we call this one tautology, and tautology is always true in this case, and we mentioned that this one will be the satisfying condition for the equivalency in this case. All right, let's move a bit for some terminology. Satisfiable. When should we say about an assertion or proposition satisfiable? If it has at least one true value. Think about and. If you have P and Q, we have only one and when both of them are true. This is satisfiable. A tautology, if it's always true, I just mentioned about it. If it is always true, then it is a tautology, and tautology in this case means the outcome of an operation is always true. Now, imagine this, P or not P. This will produce always true in the outcome. You can check it by yourself. Okay. Contradiction is always false, and there is a very common and easy example for it. P or not P. opposite to P or not P. This is always true, while the other one here is always false. And it's contradiction in this case. We have something we call contingency. Contingency is actually a more general type of satisfiable. Why? Because it's neither tautology nor contradiction. It may have several falses, several truths, but it's not always true. Neither is it always false. All right. Let's discuss the laws we mentioned earlier, the distributive law. Distributive of what? Distribution of and over or distribution of or over and. This one, distribution of and over or, is just straightforward, similar to the mathematics we learned at high school. We distribute P and Q, or P or Q, or whatever in this case are. So P and Q, or P and R. Distribution of and over or. For the proof, you can check actually your textbook. I'm not going to prove it now, and usually I don't ask these questions, but it's extremely intuitive. You can check how it would be intuitive. In order for us to satisfy a certain outcome here, or maybe you can think about only true or truth value. Look, we have and here, and these two should be true as well as P in order for us to get true. Or individually, P and Q should be true, or P and R should be also true at the same time, or one of them. This is just intuition, it's not a proof. It's not, just an intuitive representation of the proof. The same goes for the distribution of or over and, P or Q and P or R. The same thing applies. You can check truth table or you can check your textbook for the proof. I'm not going to ask it, but for your own knowledge you can go through them. We have De Morgan's laws. We have two of these laws, the negation of anding statement and the negation of oring statement. This is the negation of oring statement. Q or R, if we negate all of them, remember parentheses here, it would be exactly like anding their negations separately. Not Q and not R. The same thing goes for anding. If we are negating this and process here, it would be the negation of the individual assertions or statements, P and Q, or prepositions, but with or as an operation in between. Not Q or not R. That's just move forward. Now you can prove this one using truth table, or you can also check the proof from your textbook. Use it as just a task or a duty. Check it from your book. You can use truth table. I told you about truth table. It's easy actually to check, to confirm whether these hold or not, whether they are true or not. Actually, it's available here. I don't want to go through it. It's easy. We don't want to waste our time here. You can go through it for your own practice. All right, let's go to other laws that we usually use for simplification, and usually I ask questions, and I will show you what type of questions I ask, and there will be a tutorial, don't worry. I also promised you about the first chapter of a tutorial. I'll combine both of them within this week. Hopefully very soon I'll produce 2 tutorial sessions. Until then, let's just carry on here. We said earlier about a tautology statement, P or not P is always tautology, is always true, or a tautology. And in that case, this is referred to by excluded middle law, all right? And this is contradiction law. Contradiction always false, contradictive, or this statement is contradiction, it's always false. P and not P is always false, no matter what. You would never get anything other than false in this case. Identity laws, who holds the identity? So if we say P or F, F here is irrelevant. P will hold itself the way it is. Whatever, if it is 1, it will be 1. If it is 0, it will be 0. Or if it is true, it will be true, remain true. If it is false, it will remain false and nothing will change. The same goes to P and true. and in this case true will not affect the whole operation, and P will hold its own identity. Domination, which one is more dominant? So here is about dominance. So which one is more dominant? P or T. If you OR true with anything, it is true. And if you AND anything with false, it is false. So this is the dominance. Anything means either true or false, it doesn't matter. Alright, let's move on. Idempotent laws. P or P, P and P will get you back to P. The double negation, if you negate twice, or if you apply not twice to anything, it will take you back to the same process. Now, they are equivalent, yet they are not equal. I highlight and repeat again. Why? We have double negation here. These are two operations. P by itself is just an assertion, so we have two operations to get you back to P. You get the same outcome, but the whole operation is not equal. It produces the same outcome. It is equivalent. Okay. Let's go to commutative law again here. What we have, if you have P or Q, you can shuffle them. There is no problem. Q or P. Same goes to AND. So it's P or and Q or Q and P. There is no difference. This is commutative law. Okay. We have the associative laws. Now what we have, P or Q or R. Now what you want, let's say you are interested in dragging R inside and throwing P outside. It's possible, and that's fine, as long as these are one type of operation. They are the same, either or like this case, or and like this case. This is what we call associative. If there is a change, then another rule applies. We will see it in a while. Now look at the distributive law. Distributive of what? We said earlier, either or over and, or and over or. Now look at this. Remember, now we may have something like a common assertion. Now this is a special case. If we have a common assertion, now we have P or Q all and P or R all, as in parentheses. So P is common, remember. It would be P or Q and R, the distribution of or over and. Alright, the same goes to if we have again a common P for both parentheses here, and we have the distribution and over or. Here would be P and Q or R. It's extremely straightforward and easy. The De Morgan's law, the negation of and or, we explained about them. The absorption laws, it's very similar to the distributive, but it is not distribution in the literal meaning. Rather, it is P or, now look at this, P and Q. So in that case, what we are getting back is P by itself. We absorb this process. That's why what we refer to it by absorption. P and P or Q, it also P absorb the process here, or this part of the operation. Let's take a simple example. This is a proof. You can go through the truth table. I'm not going to do it. You can do it because these are actually elementary. We are not going through 1010. This is bitwise operation. So you can just go through it and see, or you can try to prove it mathematically. If you cannot, ask me, no problem, I'll explain it to you. We will have a live session very soon, hopefully starting from next week. Or I can present it to you in the tutorial, and that will be another part. This is the type of questions I usually ask during the exams or quizzes. I bring you a compound statement like this, and I tell you simplify it or prove that this statement is equivalent to another statement. In order for us to simplify it, start by this. This is easy. Why we start here? Double negation for this one. Actually, negation of ending, then we have double negation. So what we have, ignore this one. You can think of it as just one statement with no not. So we have a De Morgan's law, right? Here we have and. Think about this one, X and Q. apply De Morgan's law, not x or not q. Alright, x itself equals not p, so we will end up having like something like this through De Morgan's law the first, then after that will be double negation. For the double negation we get back p or not q. Well, up until now is easy because just double negation and De Morgan's law the first, then double negation. But now, how about now? Now look, this is common, p, and for this reason we have the distributive law applies, distributive of or over and over and in that case what we are going to have p or q and not q. Now, do you remember q and not q is always false? This one is like false, just f statement, always false. And what's left? P or false, and that's the dominance in this case. P is dominant in this case, and what we will get is the identity. We will get back to P itself as an identity. When you OR a statement with F, it's always the same statement. The identity takes back the same statement. What did we reach here? What did we achieve? P. So for sure it's much easier than this, even for implementation in computation. I may ask you something like this. Prove that this expression is equivalent to this. And this is a common question usually I ask. Predicates. Not every statement we can represent by compound logical statements with connectives or whatever, and or. Sometimes we need to have special types, not only one type, special types of logical operators or operations to represent assertions or compound assertions. What do I mean? Now look at this statement. Every computer connected to the university network is functioning properly. Now, the problem is every, how do we represent it? Or, and, no, if, no. So this one is not applicable by the operations we studied, and this is what we will be addressing, the predicates. Now, in order for us to present the predicates, let's just think about a simpler way to visualize what we said, every computer connected to the network is functioning properly. Now, what we can say by simple propositions, we can say computer 1 or computer A is functioning properly. This is possible. Okay, computer maybe 2 is functioning properly. All right. But for all or every or many or some, then we have to go to what we call predicate logic. We have their own operations. In order for us to understand predicates, let's go to basic mathematics. You guys are familiar with those, but let me just address it from logic perspective. P of x equals x less than 5 means what? This is a predicate, okay, or a logical statement that asserts certain outcome based on an equation. Okay. Now, x less than 5 may be true, may be false. It depends on the value of x. So in order for us to know if this one is true, then we need to know the value of x. Now let's say P of 1, 1 less than 5, that's true. P of 6 less than 5, that's false. So in order for us to know, we need to check the value of x first, then we can say the statement is true or false, and this is a predicate in this case. A statement represented by a certain mathematical equation or a relevant representation. Let's just take other examples. P of x is represented by x is a multiple of 5. This is easy, like 5 times x. X could be any value in this case. Of course, integer. I say any integer value. Okay. When will it be true? If we multiply 5 to x here, and then in that case it will be multiple. If we are considering, of course, integer in this case. Let's take another predicate. P of x equals x plus 1 greater than x. Now, what we are looking for is the evaluation of this structure or statement. If it is true or false, it depends on the value of x. Is it true? Of course, x plus 1 is always greater than x, no matter what, and this is always true in this case. All right. How about the last one? X plus 3 less than minus x. This is easy. You can take x to the side and find out where exactly it would be true. If you are using real numbers, I haven't yet explained about those in discrete mathematics. We will take them very soon, but real numbers, actually numbers with decimal points. Integers are numbers with no decimal points, just the numbers that we use for counting. Okay. But they may include the negative side, they may include positive side. Usually we use the positive integers, especially for counting, like we human beings count 1, 2, 3. 0 is not included in most of the case of positive integers here. All right, we do not consider it as a count. That's why it's not included. All right, now if we are saying this one is real number, x is real number, then well, minus 3 over 2, that will be whatever less than minus 3 over 2 will hold this one true. You can try it yourself. All right, let's take other values or other predicates and see how things work. Let q of x and y denote the statement x equals y plus 3. What are the truth values of the propositions q12 and q30? In brief, or in actually simple words, what you need to do is just substitute. Substitute what? 1 for x, 2 for y for the first one. 1 equals 2 plus 3, that's false. All right, let's take the other one. 3 equals 0 plus 3, that's true, and that's it. That's it. All right, let's take another example, a little bit more about discrete mathematics logic. Let A, C, and N denote the statement computer C is connected to the network N, where C is a variable representing a computer and N is a variable representing a network. So a computer and a network, computer A is connected to network, computer C is connected to a network A, and this is a predicate in this case. All right. Suppose that the computer math1 is connected to network campus T, but not to network campus 1. What are the values of A math1 campus 1? Well, it is not connected to campus 1, so this is false. And A math1 campus 2 is directly connected to campus 2. This is true based on these assertions. And as you see, the representation here of the predicate is much easier than a whole explanation in natural language. Okay, so what are these predicates good for and what can we use them for? We usually use them for pre and post conditions. You guys are familiar with pre and post conditions from principles of software engineering. I explained to you about them. Also in Java we studied somehow about those. For testing purposes, we check the conditions. Every, let's say, statement, every condition holds, and so on. All right. We have another part other than the predicate. We have something we call quantifiers. Quantifiers, I said earlier, when I refer to every or many or all these things, how we express them. I explained about predicates. Why? Because they are important before we go to quantifiers. Why? We generalize usually predicates by using quantifiers. So in order for us to have all, some, many, none, a few, and so on, we have to use quantifiers. We have different types of quantifiers. We will address these two. Universal. Universal means each and every one in the group or the set under consideration. So if I say every student in my class, this is universal. Why? The universal set in this case, we haven't yet explained about sets, but you guys are familiar with sets. Yet we will explain about them in a while. Just consider that our, let's say, class, this discrete mathematics, is a set. So when I say every student or all students in my class, this is universal. We speak about each and every one. Existential tells at least about one, only one. I say there is at least one in my course of discrete mathematics, or in your course in discrete mathematics, for example, is not attending. So this is the way we say quantification, we have universal and existential. If you have not yet got the idea, just listen, you will catch it very soon. Now for the universal quantifier, we represent it by upside down A, and it means all, or for all values of certain set. Now, what is the point with predicates? Now back again to predicates, and now you will start linking the points to each other. P of x equals x plus 1 greater than x. So we are representing a predicate here by this assertion. It may be true, it may be false, depending on the values of x or the assigned values of x. Now, what are the assigned values of x? Well, if I say for all values of x, how do we translate it in English? We have two common ways to do that. For all values of x, px is true, or the predicate px is true. Or if you want, you can ignore px and replace it by its own realization. For all values of x, x plus 1 is greater than x is true. And this is true in this case, always, yes. All right. Of course, we are considering real numbers or maybe integer numbers. Now, how will I address and check each and every number? In real numbers, I can't do that. It's not possible. So sometimes, in order for us to prove that it is true or not true, false, we can just get something we call counterexample. Counterexample means what? Just one case that makes the whole quantification, not predicate, means the whole quantification here, is false. So we say for all values of x, px is true. If you get one which is false, then the whole quantification is false. All right, let's take an example. Qx, let Qx as a quantifier, as a predicate, sorry, is equal to x less than 2. All right. Now, in order for us to check for all values of x, Qx is true, where the domain here, what applies to x, what we substitute for x, for all real numbers. Well, for all the real numbers, x less than 2, that is not true. How do I know? If we get one counterexample, that's enough. Now think about we say less. Think about 3. 3, is it less than 2? It's not. Then you have a counterexample. This is just one example. You can take 10, you can take, maybe even this is real number, right? Real number, so we can take 2.001. That's enough for you to satisfy the condition that one counterexample is available. There are so many, but one is enough. And that makes the whole statement. Why? Because for all values, one counterexample is enough for you to make the whole quantifier here false. Okay. Now, let's say we have discrete elements in one set. In order for us to check the validity or the truth value of a quantifier, we need to AND all of them. What does it mean? Now we say for all values of x. What is x? Discrete values, x1, x2, x3 until xn. Then we have to substitute all those, then take their AND. Why? Because one of them, if one of them is false, then the whole ANDing process will produce to us false. Okay, this is ANDing here is a conjunction, if you remember. Disjunction or conjunction is AND. And in that case, in order for us to ensure the whole predicate, the whole quantifier, not predicate, the whole quantification or quantifier here is true, all its elements must be true at the same time in order for us to get the truth of the universal quantifier. Take an example. What's the truth value of for all values of x, px is true, where px is the statement x squared less than 10, and the domain consists of positive integers. Now remember, positive integers start from 1 and go onward, not exceeding 4. That means 4 is included. So 1, 2, 3, I'm sorry about this typing, and 4. All right. So in this case, we have only these four discrete elements. We take their predicate and find 1 squared is 1 less than 10, that's fine. 2 squared is 4 less than 10, that's also acceptable, true. 3 squared is less than 10, that's also true. 4 squared is 16. So if we add this one, this is true, this is true, this is true, but this one is false. This takes us to the statement or the fact that the whole quantification here is false. Why? It's universal. If 1 is false, it's adequate, it's enough to make the whole quantifier false. All right. Now for the existential quantifier, it's somehow the opposite way of the universal. The universal says all elements. Now here we don't look for all elements, we look for just one element at least. There exists an element. There is a value of x that makes the predicate true. And this is what we refer to by existential. How do we represent it? By this, in verse E, and it is said or mentioned the existential quantifier. There exists x or value of x that makes the predicate px true or makes px true. All right. Let's take some examples. Let px, or the predicate px here, x greater than 3. What is the truth value of the quantification for there exists value x makes px or such that px is true? Well, do we have the domain consists all real numbers? Do we have any value? If we substitute it in x here, makes the whole predicate true. Think about 4 for all real numbers, or maybe 3.1. That's enough. If you get only one value, it's opposite to the counterexample. You get one false value that makes the whole universal quantifier false. But here in this case, existential, you get just one true value. That's enough for you to get the true value of the whole quantification. And here, if you just substitute whatever value greater than 3, in this case, what we have here for 3, we have maybe 3.1, whatever, 3.5, 3.5, whatever. Think about 10 million, any value. Just one is enough, adequate to make the whole quantifier true. Let's take another example. That qx denote the statement x equals to x plus 1. Is that mathematically possible? It's not. So for this case, what we say is, what's the truth value of the quantification? There exists value x or x such that the quantifier qx is true in the domain of real numbers. We speak about real numbers. It's not possible. You can't get a value for x that equals to itself plus 1. That's not possible mathematically in real numbers. And in this case, this is false. If you try, whatever you try in the real numbers, you'll never get any value. All right. Now, in order for us to represent the existential quantifier and check its values, if it is discrete or composed of discrete elements. Discrete elements means what? We have a set of values for the predicate, and we need to check each and every one to confirm maybe one of them is true, so that we check the whole predicate is true. We can apply the disjunction or ORing operation. Opposite to the universal, we applied ANDing or conjunction. Now, what we do here is we check the whole domain. Let's take an example, a quick one. What's the truth value of there exists value of x such that px is true? What's px? Px is the statement x squared greater than 10. And the universe, now look, the universe, the whole set, what we have, is the discourse consists of positive integers, so start from 1, what we took earlier, not exceeding 4 1, 2, 3, 4. So this is my set, and I need to apply each and every one to get at least one true. All right, x squared greater than 10. 1 squared is less than 10. 2 squared is less than 10. 3 squared is less than 10. However, 4 squared is 16 greater than 10. So this is true, and it's adequate to make the whole ORing operation here is true, and that makes the existential quantifier true in this case. All right. The uniqueness quantifier. For existential quantifier, we have a special type of quantifier. We call it there is only one uniqueness, just only one element that makes the predicate true, and in that case we refer to it by uniqueness quantifier. Well, this is a special case. It's also still an existential quantifier, but because we have only one in that case, we refer to it by uniqueness quantifier. Look at this example. There exists only one value. There is only and only one value for x such that x minus 1 is equal to 0. That's for sure. Why? Because x here in this case equals 1. There is no other value in real numbers that will satisfy this formula or this equation. All right. If you find such a thing, only one value like this one, in this case, only one value, this is also uniqueness. All right. There exists only one value in this case. So if I put this one 1, it also applies. Okay. Right. Now, sometimes what we do is like this. If we have different predicates and quantifiers, if they are involved with combinations, what we can do, we can distribute. Now look at this. For all values of x, now we have p of x or px and qx. You can distribute the quantification here. For all values of x, px holds true, and at the same time, for all values of x, qx holds true. Right? This is what it means. All right. Now, how about the negation? If we negate a universal quantifier or an existential quantifier, what happens? Now look at it. We will discuss it from well, natural language perspective and mathematical perspective. Now I open a bracket. For all values of x, px is true. Not. That means, what's its negation? If not all values, for all values of x, px is true, then at least there's one value, that makes px not true. So what happens here? The negation of the existential quantifier takes us to takes us to the existential quantifier, and the existential quantifier of what? Px must be also negated. Now look at this. Every student in your class has taken a course of calculus. Every, that means all students. If we negate it, it would be existential. There is a student, or at least there is a student in your class who has not taken a course in calculus. This is the negation of the statement. So we will not go to play the game of natural language. It's really hard and it needs concentration. We will play with the basic discrete mathematics rules, easier for us and for the computer. We do the same for the existential. If you negate the existential quantifier, it goes to universal quantifier of the negation of the predicate, and they are summarized here. If you explain about this, look at this. For every x, px is false. Okay. Now, it would be false if there is x for which px is true. That's what we are referring to exactly. And the same goes to the universal. If you negate it, it would be existential, and the existential of the negation, there is an element, at least an element, an x at least, for which px is false. So px will be true for every x if it is false. Now we are not checking if it is false or true, but the meaning and how we apply it. Now let's just take a simple example here. What are the negations of the statements for all values of x, x squared is greater than x, and there exists x such that x squared equals 2. Alright, let's just consider in this case integers. Let's think about integers, integer values. Now if we negate, we need to negate. If you want to think about the truth value, we would consider integers, just an assumption, but we need, what are the negations? So if you negate this one, now what happens? There, for all values, or for every x, or values for all values of x, x squared greater than x is true. Negate first will be this one would be there exists x such that not x squared greater than x. So what does it mean? Not x squared greater than x. In other words, this will be x squared less than or equal x. This is the negation of this whatever inside the parentheses. Existential, according to the rule, universal will be negated to existential, and this x squared greater than x will be x squared less than equal x. Let's take the other one. The existential will be negated to universal for all values of x. Negate x squared equals to 2. It would be x squared not equal. This is its negation, not equal to. And you can check the truth table. It depends on the domain. You can think about integer and see what's the truth table. Sorry, not truth. What is the truth value in this case? Will it hold or not? As I said, if it is not mentioned, you can assume it, but you have to mention. Like, you know, we are considering real numbers. We're considering, let's say, integer numbers, and so on. This is the end of this chapter. There will be a third and final part, and then we will have 2 extensive sessions for tutorial. Until then, have a good time. Goodbye.